All right, so quickly sketch 2 cycles of f of x equals 3 sine of 2x. What's the parent function here? Yeah, you could say sine. That's fine. That's still legit. Or you can say sahala, right? And so the 3 and the 2 are two values that are going to modify the original graph of sine. What is the 3 going to do? Good. Vertically stretch it by a factor of 3. And of course, that ends up being our value of the absolute value of A, which is our what? We call it the amplitude. Yeah, but it works the same way. It's going to be a vertical stretch by a factor of 3. The graph is 3 times taller. The 2 does what to any graph, including this one? Horizontal compression by a factor of 2. It's our B value, which means we're going to see 2 cycles now in 2 pi. That's what the meaning of B is. It's kind of like a frequency, which makes sense. If we're going to see 2 cycles in 2 pi instead of 1, they each have to be half as wide as they previously were. The C value, like yesterday, is 0. There's no phase shift. That's nice. The D value is 0, so the sinusoidal axis is still the x-axis, but the period is what we want to find. And remember, the period is 2 pi over the absolute value of B, which is 2 pi over 2, which is pi. Makes perfect sense. Because the previous period was 2 pi, now we got to fit 2 of them in, so now they're half as wide as they used to be. So now that we have all that information, we can go ahead and create the graph. So just draw a little x and y axis, and then you want to come out some arbitrary length here, maybe not quite, maybe 2/3 of the way, and you call that, not 2 pi, my bad, you want to call that whatever the period is, because I'm only interested in you sketching 2 cycles. So I'd rather you stretch out each cycle and label it appropriately. And so in that case, you come out here and call that pi. And once you have that distance from the y-axis to pi, that's the length of 1 cycle. And of course, you need 5 critical values, but there's going to be 4 intervals. So you can actually bisect it and label it, and then bisect it and label it. And now you have pi fourths as your quarter cycle counting interval, and you have the distance on your iPad/paper that you want to preserve then for all your other critical values. So now if you just keep adding critical values that are about the same distance apart, and again, you're just eyeballing it. You don't have to use a ruler or anything. But now you can label every single one of those because you're counting by pi fourths. So we have 0, 1 pi fourths, 2 pi fourths. The next one will be 3 pi fourths, 4 pi fourths, 5 pi fourths. The next one is 6 pi fourths, which simplifies to what? 3 pi halves. And then 7 pi fourths, so on and so forth, going out to the right. If you have more room, put more dots or hash marks. When you come back to the left, then it's negative pi fourths. Negative 2 pi fourths is negative pi halves. Negative 3 pi fourths. And negative 4 pi fourths is negative pi. So that's just how many points that I had room for.
So the negative, you don't have to put that many check marks?
No, you're gonna need like 10 marks to get 2 cycles in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have a couple of extra. I will always have you sketch at least 2 cycles and always have you sketch at least 1 point to the left of the y-axis. So if you wanted to start at negative pi fourths and then keep going out to the right, that's fine. All right, so that sets up the x-axis. Now to set up the y-axis, since the amplitude is 3 and the sinusoidal axis is 0, we're going to go up 3 units from there and down 3 units to there. And we put those marks right there. And now it's time to put our graphing values on there. So I'll choose, let's see, we'll choose that color. And this is then a parent function of sine. So sine is sahala. So it's axis high, axis low, axis high, axis low. And then you continue it back the other way. Going back to the left, it would be low, axis, high, axis. Something like that. And then it's just a matter of connecting the dots with your correct curvature. So again, I always sketch them in quarter cycle intervals so that you can exaggerate the curvature change. And then I would like if you always turn the corner or extend out and draw little arrows just to show that the graph continues on. And that's it. That's all you have to do. All right, any questions on that one? We have 2.5 cycles shown there, which certainly is at least 2. So that's what we did yesterday. That's a pretty easy variety because we're just dilating, stretching, and compressing. It doesn't change the critical values because we're not shifting it left or right. And it doesn't change the sinusoidal axis because we're not shifting it up or down. All right, any questions on that one?
I just have a question.
Yeah, fire away.
The horizontal shift left to right, how do you know where your starting point is, I guess?
Good question. We're going to look at one like that right now, and I'll show you how to do that. Yeah, if there is a horizontal shift, you just have to be careful because if you're sketching by the Sahala or Chala method, that first critical value has to reference either the y-axis if there is no phase shift or where the y-axis moves to if there is a phase shift. It always has to reference that original y-axis point. All right? Okay, so let's jump down to example 6, and you'll see one of those. Sketch at least one cycle. Again, disregard those instructions. We'll sketch 2 of f of x equals 3 sine of x minus pi halves minus 2. So what's the parent function here? Sahala. All right? Now let's go off to the left and kind of take inventory again. We got the absolute value of A, the absolute value of B, C, D, and P, just like the alphabet song. What is our amplitude? 3, okay? So it's going to be up 3 units and down 3 units from the sinusoidal axis, whatever that is. What's our B value? Remember, B is the value that's being multiplied on the inside. It's 1, good, because the inside is that, and it's just 1 times the quantity x minus pi halves. That's nice, because now we're going to see 1 cycle in 2 pi, which means our period hasn't changed. So the period is just 2 pi over 1 or 2 pi. So in this one, we're not stretching or compressing horizontally. But now we have a C value. And C value, remember, the standard form is x minus C. So C is technically pi halves. But here's what I want you to do for the C value. These are just like little notes to yourself to help you sketch it correctly. And I do want you to write it out. I'll be grading it. So what's more important about the C is not whether it's plus or minus, but which direction you're going to move. So x minus pi halves will move the graph to the what pi halves units? Right. So that's what I want you to write here. We're moving it right pi halves units. And the D value is -2, but again, what is that going to do to the graph? Move it down 2. So that's what you're going to write. Down 2. All right? The same thing you would say if you had a dog that jumped up on guests whose name happened to be 2, right? You'd say down 2. Down 2. All right, so we can set up the y-axis pretty easily because we know now our sinusoidal axis is down to 2, and from -2 then we're going to go up how far from there? 3, and then from -2 we're going to go down 3. So notice we can actually do something else. A, B, C, D, D, P, R. We can actually find the range without sketching it. Here's how we find it. It's going to be the sinusoidal axis, which is always D, minus D amplitude for your lower bound, and your D value plus the absolute value of A, your amplitude, to get your upper bound. So for us, we're down 2, so we're at -2. And like we just said, we're going to subtract 3 to get to our low point. And then for our high point, we're going to start at the sinusoidal axis of -2 and go up 3. So the range is -5 to 1. Now, there's a couple of reasons you might want to figure that out beforehand. Actually, 3. Number 1, I'll have you do it, and I'll grade it. Number 2, on a multiple choice, I might just ask you for the range of a function. And you can find it pretty easily without having to go through the elaborate setup of graphing it. And the third reason is when you are trying to graph it, you can kind of decide where you want to put your x-axis, okay, because you do have limited space. Most of the graph lives in negative land and only one value above. Okay, but now we need to think about what the critical values on the x-axis are going to be, because they're not going to be the same ones they used to be. We're shifting everything right pi halves. So anytime you have a horizontal shift, if you have a C value that is not equal to 0, you need to make what I call a sacrificial x-axis. Okay? Kind of like you're an ancient Mayan and you're kind of trying to appease the math gods and to make a sacrificial x-axis. Because on your final graph, I want to see nothing but your final critical values. So that's not the place to do your scratch work. So here's what I mean by a sacrificial x-axis. Okay, this is 0. I'm not going to draw the y-axis in its entirety. So what did we do previously? We went out the length of the period, which was 2 pi. We bisected it and got pi. Bisected that and got pi halves. Pi halves, before the shift and after the shift, is going to be still the most important number. Because even if you shift it left or right, you're still going to have your values pi halves apart. Your next number over here then would be 3 pi halves. Now here's what you can do. Your y-axis is normally at x equals 0. We're shifting everything right pi halves units. So our y-axis moves to the right from 0 to what? Pi halves. Now this is an easy shift. They're not always going to be this easy, but because it's the first one, I gave you an easy one. So what's nice about this is if we had our old critical values, all we're doing is we're picking the entire graph up one critical value and setting it back down. So the old critical values are still critical values. We don't have to make new marks, but we have to reference pi halves now for the Sahala-Chala method. We'll have some later on where we actually have to make new marks. All right? But for now, we've just kind of thought about it. We're going to start at pi halves, and those are still the critical values. And so what that means is we can go straight to our final graph. So there it is. Now, because most of my values were negative, right, for the y values, negative 5 to 1, I'm going to draw my x-axis just a little bit above the center. Makes sense. It's up to you. And now I can go out here, and I can still call this 2 pi. No big deal. 2 pi. Half of that's pi. Half of that's pi halves. It just so happens I can use the same numbers. But again, that's not always the case. Because I shifted everything right pi halves, and the old y-axis was at 0, and I just picked it up and moved it right pi halves, which is the very next critical value. So the value at pi halves moved over to pi. The value at pi moved over to 3 pi halves. So again, I'm picking it up and moving it over one critical value and setting it back down in the same tracks. All right, so now what I would do is I would draw a dotted line or a dashed line, whatever you want to do, at pi halves. It's not a vertical asymptote. It's just a reference line, an imaginary reference line that tells us that that's our new y-axis for the Sahala-Chala method of graphing. All right? Now let's add a few more critical values. So we'll try and preserve that distance the best you can. Don't forget we still have 0. There would be negative pi halves. I'll add one more to the left here. It would be negative pi. And what the heck, one more out to the right. So now we just label them by counting by pi halves. So 3 pi halves, 4 pi halves, this would be 5 pi halves, 6 pi halves, 7 pi halves. So setting up the x-axis could be the most labor-intensive of sketching these things. But in this case, it was still relatively easy because we moved the graph over one critical value. So the dotted line there represents our what? Our new y-axis. Good. Now, let's set up the y-axis. We went down 2 units. So the sinusoidal axis, which is always on the x-axis, gets moved down 2 units as well. So there's negative 2. And what I want y'all to do now is draw a dotted horizontal line that is not only the sinusoidal axis, but it's your new x-axis as well. So notice your new origin is at the point pi halves negative 2. That's your new origin. Okay? Now to get the values on the axis, you're going to go up 3 and down 3. And we've already done that. So if you go up 3, you go up here to negative 1. And once you establish that distance from the sinusoidal axis to the high point, you need to try and preserve that. You go down 3 to negative 5. This is the only information I want you to label on your graph. Every critical value, sinusoidal axis, and the high and low. Any other values on there, you're going to lose points because it just overly and unnecessarily clutters the graph. Now at this point, this could accommodate either a Sahala or a Chala transformation, either one. The only difference is where you start. We started with a Sahala, okay? And so we need to start on the axis. And remember, there's two places to go from the axis. From the axis, you can either go up or go down. Sahala says to start on the axis and go up. Good. So let's go ahead and do that. Our axis is going to be right there at the point pi halves negative 2. That's your new origin, and without any shifts, that's where sine would start. So that's why it's important to draw those two new y-axes and x-axes. Now from there, you're going to go axis to the right, pi, which will be at pi halves 1, back down to the axis at 3 pi halves negative 2. So you're not on the x-axis anymore. And then low, so you have 2 pi negative 5, axis 5 pi halves negative 2, 6 pi halves, which I didn't simplify to 3 pi, but it does, and then back down to the axis. And then you work back to the left. So we still have a critical value at 0, so we have a point negative 5, 0. And then we have negative pi halves, and then negative pi 1. So there are your critical values. And now it's just a matter of connecting the dots again. So notice your inflection values are now on your sinusoidal axis, not the x-axis. It should look perfectly symmetrical above and below that sinusoidal axis. So turn the corners or extend past the critical value and draw little arrows. And there you go. All right, so there's the graph. And once you have the graph, I can ask you to do all kinds of things, like what's the range, of course, negative 5 to 1. But what is the location of a local maximum? X equals pi, 3 pi, negative pi, so on and so forth. What would be the coordinate of an inflection point? Anyone? Negative pi halves negative 2, pi halves negative 2, 3 pi halves negative 2. Any point on the sinusoidal axis would be an inflection point. I could ask you on what interval is the function increasing, and you could say from x equals 0 to pi, decreasing from pi to 2 pi, so on and so forth. Okay, one of the things that we're going to do once we have this is to write an equivalent equation in terms of the cofunction. Because remember, sine and cosine only differ by what? Their graphs only differ by pi halves, which is 90 degrees. We generated this graph from a sine graph, yes? But I claim that we can write an equivalent equation in terms of its cofunction, cosine. Now, the only thing that's going to change if I want to write it as a cosine function should be the what? A, B, C, or D value? The C value. That's the only thing that's going to change. Because the graph is what it is. It has a vertical dilation of 3, so the amplitude's 3. It has the sinusoidal axis at negative 2. B is still B. The period of sine and cosine are always the same. The only difference is where we decide to start. So let's see if we can write an equivalent equation that's in terms of Chala. Well, here's why it's so nice to do the Sahala-Chala method. All you have to do to sketch a cosine function is look for a high point once you have it graphed, because cosine starts at a high point. Where on your graph do we have a high point? For what value of x? Pi. Pi, right there. At pi, we have a high point. So all I would need to do is take my graph of cosine, which normally has the high point on the y-axis, pick that graph up, that would be right there at the y-axis, and move it to the what? Pi units. I need to move it pi units to the right. Because by default, it would start on the y-axis. If I want to get it over to pi, I got to scoot the original graph to the right, pi units. Okay, so here's what the equation would be. You'd have f of x equals, 3 is still 3, but now we have cosine of x plus or minus something minus 2. So if I need to scoot my cosine graph right pi units, is it going to be x plus or minus pi in my equation? Minus pi. Good. Would plus pi work as well? Because plus pi would move at what? Left pi. Do we happen to have a high point also at negative pi? Yeah. Could you also say x minus 3 pi? Yes. All you have to do is get to any high point, and it works. You were going to ask a question, Ms. Ward?
Yes, okay, can you re-explain, because I understand like how you started the high point, so you pick any high point, in this case you took pi. How do we know we had to shift exactly pi has, because I guess,
We have to shift pi units.
pi units, because at 0, if we were just.
The normal graph of cosine without any horizontal shifts starts on the y-axis at a high point. Right. So I need to get that high point over to where the high points actually are. Okay? Yeah, let's do another thing. We started with a sine function that shifted over to pi halves. I claim we can write another function in terms of sine that gives us the same graph. Again, the only difference is going to be the phase shift. So if I want to write another equation in terms of sine that doesn't shift sine over to pi halves, remember sine normally on the y-axis starts on the axis and goes up? We took that graph and shifted it over to pi halves. All we have to do is find another place on our graph where we're on the axis going up. Anyone see one? 5 pi halves. You have to be careful. You can't choose 3 pi halves because that's on the axis going down. There's 2 places to go from the axis. But if I get over to 5 pi halves, that's an axis going up. So again, if sine on the y-axis by the Sahala method starts at 0 going up, I need to shift it to the right 5 pi halves. So would that be plus or minus 5 pi halves? Minus 5 pi halves. Good. Oops, that was not really well written. 5 pi halves. Now let's see if that's actually correct. I could be lying to you, and you could just be agreeing with me, like, okay. But if we graph them on the calculator should confirm that they are in fact the same, right? For if I graph all 3 of these equations, how many graphs shall I see if they are in fact the same? 1. They will trace out on top of each other. Okay? So all we have to do is wait for this to load. Now what mode should we be in? Radian. You could be in either mode when you're graphing the sinusoid, but if you're in degree mode, you're going to have to make your x and y axis a lot bigger, because by default it's negative 10 to 10. And negative 10 degrees to 10 degrees does not see much of a cycle, does it? But negative 10 radians to 10 radians is a lot more, right? That's more than 1 full rotation on the unit circle. That's why I want to do it in radians. So let's go ahead and just flush the toilet here, get a clean bowl. There we go. And we'll go ahead. That was gross, I know. All right, so now I'll type it in. 3 sine of x minus pi halves, pi divided by 2, and minus 2. Now, the nice thing is we don't have to hit zoom 6, which is your standing viewing window. We have spent a lot of time and resources this morning coming up with the beautiful scale for our x and y axes, yeah? We might as well graph it in the same window so that we can compare apples to apples, right? So let's do that. I'll go to my calculator. Calculator, I said. Okay, and I'll go to the window. I'm going to go from negative pi, because that's where we went to, I went up to 7 pi halves. So my x max will be 7 pi divided by 2. If you want to put your x scale to pi halves, that's not going to hurt. That's how often we had a tick mark for our critical value. The y min was negative 5, but I'm going to go like to negative 8. You always want to buffer that. And then instead of going up to 1, we'll go up to maybe 4. And I'm just going to turn my y scale off. I really don't care to have tick marks. Now, when I hit graph, I should see something that resembles what we sketched, right? If not, it's probably the calculator's fault. Ooh, fun. Looks pretty good, doesn't it? Looks pretty good. If you want, you could graph, and let's do y3 because it's going to graph in black there. Let's go ahead and graph y equals negative 2. That should graph as what type of function? Horizontal line. That's the sinusoidal axis. Does it look equal above and below? Yeah. Okay, so let's go ahead. The moment of truth. Let's type in our cosine function. 3 cosine, parentheses opened, x minus pi, close it, minus 2. If it's truly the same graph, it should trace out the blue graph with red. Here we go. Enter, enter, enter. Oh, I got to hit graph. Okay. Ooh, ooh, hey. Now there's visual confirmation, but of course if you go to the table, which is second graph, you'll see that it generates y values. And if you go to the column itself, you can see that it has more decimals there. So if you click left and right and toggle left and right, are they the exact same y values at the same x value? Yes, indeed. So there's great confirmation. And then let's do it one more time. Let's use, you want to use pink or green? Green it is. Good. We'll type in 3. They didn't say anything. I chose for them. Okay, this if you're watching at home. Let's do 5 pi halves minus 2. So now it should trace over the red graph in green. You ready? I'm ready. You ready? Anticlimactic. It's going to work. Cool. Cool. Sine and cosine only differ by a phase shift from each other. The unadulterated versions only differ by pi halves. Once you start compressing or stretching them, they will only differ by a phase shift. So the Sahala and Chala method are great because all you have to do is look for the type of behavior you would normally expect to see on the y-axis. For cosine, high point. For sine, axis going high. And then get over to that point. All right, questions on that? Fun, 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 or fun, 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 fun? Yes, CC. I protected Cooper's identity by saying CC. D of P? On letter B. Letter B. Well, I will specifically ask you, this is just for us. I will have you fill that out. But I will ask you specifically, how many cycles does this function have between 0 and 2 pi? And then you would say B, whatever the B value is. So yeah, good question. I do want to see right pi halves and down 2. But if you just put B equals 1, that's fine. All right. Now, what would have happened if our A value was negative? What does a negative A value do to any function, like x squared and negative x squared? Reflects it across the x-axis. Good. And because your Aunt Sally is always watching over you, kind of creepy, you have to do your order of operations in her order, right? Please excuse my dear Aunt Sally. So you have to do your multiplication before your addition, which means that your A and B, your dilations and reflections, have to always come before your shifts. So if you had a negative amplitude, that is going to change Sahala into what? The axis points will stay the same because they originally are on the x-axis. But what happens with the highs and lows when you reflect across the x-axis? They flip, right? So if you happen to have a negative amplitude, we'll say it's negative sine, and the axis points stay the same. But what happens with the highs and lows, as we already said? They switch. So a high becomes a low, and the low becomes a high. And now you get Sahala's bizarro twin, negative Salaha, or negative Sal-aha, as he likes to call himself. He thinks he's clever. Negative Salaha. Now, you don't have to remember negative Salaha, do you? No. Just remember that anytime you have a negative amplitude, what happens with your highs and lows? They flip. And that's only then going to matter at the very, very end when you put your critical values. All right? Same thing with cosine. If we take Chala, remember it's Chala, not Chala, and you make the amplitude negative, now the highs and lows are the only thing that flip. So high becomes low, and low becomes high. And you end up with negative Klahal. Klahal. It's kind of a harsh A at the end. Klahal. Do you have to remember negative Klahal, the bizarro twin of Chala? No. They're bizarro twins. If you've ever watched the DC comics, every superhero has a bizarro twin on the other side of the world, which is their nemesis, their foil. So yes, these are nemesis foils. So it's probably not a good idea to even conjure their name. Just remember that the highs and lows do what if you have a negative A value? Flip. And what happens to the axis A values? Same, because they're already on the x-axis. So you have to flip them before you shift it up or down. But the way we're going to graph it is we're going to shift it up or down first, and then as we graph it, we're just going to remember that the highs and lows interchange. Okay, sweet. So, yes, but that's not how we're going to graph it. We're going to set up our X and Y axis the way we have in the past, and at the very end, we're just going to interchange our highs and lows. And the axis points, remember, the A's don't really stand for the X-axis, do they? It really means the sinusoidal axis, which if we've moved it down, we can reference that because that was the old X-axis. All right, so here we go. Example 7, we have 1 minus a half cosine of 4x plus pi. What's the parent function? That's right, chala. Very good, chala. So let's go ahead and make our little, is it in standard transformation form? No, that's actually the next step before you get going too far. You need to put it into standard transformation form. The one at the front should go at the back, so it's negative 1/2 cosine. And remember, if there's work to be done, it's probably on the inside. Is 4x plus pi in standard transformation form? No, the b value is 4, but if you don't factor out the 4 from both terms, you're going to get the shift wrong. We've done that before. So what do you get when you factor a 4 out of pi? Pi fourths. Good. So remember, the coefficient of x has to be 1 inside the shift part in order to get the shift correct. So it's actually pi fourths to the left, not pi to the left. All right, now that's standard transformation form. So we can go ahead and list our values here. The absolute value of A, the absolute value of B, C, D, P, R. Okay? What is the absolute value of A? 1/2. Now, as a note to myself, I'm going to put flip, which reminds me to flip the highs and lows at the end. But the amplitude is still 1/2. What's our B value? 4. So that's a horizontal compression by a factor of 4. How many cycles are we going to see now between 0 and 2 pi? 4. That's going to affect the period. Let's jump down to the period. You don't have to do these in any order. The period, remember, is 2 pi over b. So for us, it's 2 pi over 4, which is pi halves. That's the new period of each cycle. Do we have a horizontal shift, a phase shift? Yep. Left pi fourths. And then do we have a new sinusoidal axis? Yeah, it's up 1. Now let's go ahead and find the range very quickly. The range is going to be your sinusoidal axis, which is up 1 minus the amplitude, and the sinusoidal axis plus the amplitude. So 1 minus a half and 1 plus a half. That gives us 1/2 and 3/2, which means our graph is entirely, not necessarily optimistic, but entirely positive. Yeah. Sweet. Okay. Do we need a sacrificial axis? Yes or no? Or no or yes? Yes. Anytime you have a phase shift, you want to get your x values in order. So let's go ahead and do that. The period is pi halves. So I'm going to come over here. There's 0. There's pi halves. And then half of pi halves is pi fourths, and half of pi fourths is pi eighths. So guess what the most important value on this graph is, both pre and post shift? Pi eighths. That's how far your critical values are from each other. And then 1 pi eighths, 2 pi eighths, that'd be 3 pi eighths. So those would be the old critical values. What are we doing to each of those? We're going to move them left pi fourths. Now, if you want to create some original values to the left of 0, the first one would be negative pi eighths, and the next one would be negative pi fourths. So this one is still a relatively easy shift, right? Because we're moving our graph to the left and picking it up and setting it right back down in the existing track. We're just moving over how many critical values? 2. 0, when you subtract pi fourths, comes over to negative pi fourths. So the good news is we don't have to come up with any new x values. The bad news is our y-axis has changed. Actually, that's not bad news at all. There is no bad news. That's just more good news. So there it is. Your y-axis, your new reference point for Sahala Chala is at negative pi fourths, which is 2 critical values away. All right, so now we're ready to go ahead and put our final values down. So here's my y-axis. And because my graph is entirely positive, I'm going to draw the x-axis pretty low. Pretty low. All right, so now since I can use the same numbers here, I can just do what I previously did. I can go out an arbitrary distance, maybe about halfway here, call it pi halves, bisect, pi fourths, pi eighths. Don't forget you still have 0, and then 3 pi eighths. And now to add more critical values, just try and keep that spacing the same. And then we'll come back here to 0, negative pi eighths, negative pi fourths. And we'll just label these 1 pi eighths, 2 pi eighths, 3 pi eighths, 4 pi eighths. That would be 5 pi eighths. 6 pi eighths would be 3 pi fourths, and then 7 pi eighths. So there's your x-axis. And again, that's the most fun part of sketching sinusoid, just coming up with your new x-axis. All right, now for the y-axis, which is always easier, we're between 1/2 and 3/2. So if you want to call that 1/2 and come up here and just call that 3/2, so you can use most of the space. Now, if you bisect the high and low, that would be your sinusoidal axis, which is at y equals what? We're up 1, so there it is. The other thing I haven't done yet is put my new y-axis down, so let's do that. It was at negative pi fourths. So now your new origin is at negative pi fourths, comma 1. You see that? The y-axis went left pi fourths, as did every point, and the x-axis went up 1. Now we're ready to accommodate again either a sine or a cosine graph. Doesn't really matter. But this one was negative cosine. Negative cosine. So here we go. Normally, cosine starts where? Here's our origin. Cosine normally starts at a high point. But because it's negative cosine, we are going to start at a low point. The highs and lows switch. Okay, cool. So that's all you really need to know to get it started. So at our new y-axis, we're going to start at negative, or at what, positive 1/2. Now, because you're at a low, there's only one place to go from a low, and that's axis. And then at 0, we have a high, axis, low, axis, high, axis, low, axis. The highs and lows flipped. Cosine starts low, or negative cosine starts low, positive cosine starts high. And now it's just a matter of connecting the dots. Turn the corner, put an arrow, and then connect them with your beautiful quarter cycle arcs, and then extend past. Beautimus. Beautimus. All right, so now the real thing that's important is to be able to write equations in terms of the trig functions. We generated that as a negative cosine, but I can write it as a positive cosine. So now my amplitude will be positive 1/2 cosine 4 parentheses x plus or minus something plus 1. Again, now the only difference, aside from the sign of the amplitude, is the phase shift. So notice I left that blank. I want to write it as a positive cosine, so I have a positive 1/2. All the other numbers stay the same, but I'm going to leave my horizontal shift open for now. So for a positive cosine, I just need to look for a what feature on the graph? High point, right? It's chala. Where's the easiest high point? At 0. So if I start at 0, do I even need a phase shift? No. So one answer could just be this. It could just be, let's bring that in. It could be cosine of 4x. If you don't like that one, of course, there are other high points labeled on our diagram. You can have 4 parentheses x plus or minus something plus 1. Where's another high point? At pi halves. So if I wanted to get over to pi halves, would it be plus pi halves or minus if I wanted to shift it right? Minus pi halves. That's another one that works. Let's do one for sine. Positive sine. It's going to be positive 1/2 sine. We have a 4, x plus or minus something plus 1. So now my amplitude is positive because I wanted a positive sign. Positive sign starts on the axis but goes where? Up or down? Sahala, axis high. Where are we on the axis going up? At pi 8? Yes, no? No, that's axis going down. Negative pi 8 will work. So if I want to take my graph of sine, which normally is on the y-axis, and I want to shift it left to negative pi 8, would it be plus or minus pi 8 in my equation? Plus. Good. That moves it left. You could also say minus 3 pi 8 or minus 7 pi 8. Those also work, right?
Why is it positive 1/2 on all of these and not negative?
I'm just choosing to write them as positive amplitudes. I will have you write it in terms of positive and negative. Now, there's one guy who has his feelings hurt, right? We have a negative cosine and two positive cosines. We have a positive sine. Guess who wants to get in on the action? Negative sine. So as the bell's approaching, everything's going to be the same, except now I have a negative a value. And for negative sine, the highs and lows flip. So now we need to look for a point where we're on the axis going what? Not high, but low. Where are we on the axis going down? Pi 8 or 5 pi 8. Either one. If we want to shift the graph over to that point, we need to move it right. So I'll use the first one there. X minus, what did I say? Pi 8? Yeah. And there you go. If you want to verify by graphing all of those in the window that we graphed it in, they will all give you the exact same answer. There are infinitely many equations for any particular sinusoid. Infinitely many in terms of cosine, infinitely many in terms of negative cosine, infinitely many in terms of sine, and infinitely many in terms of negative sine. So that's like finding a needle in a needle stack if I had you write equations. There's infinitely many out there times 4. It should be easy to find at least one out of infinitely many, right? It's just which one to choose. With so many options. Okay? So again, just to summarize, if you're writing a positive cosine equation, the amplitude is positive. You're looking for what feature? High point. Negative cosine, negative amplitude, you're looking for a low. For sine, positive sine, you have to look for two things, right? You have to be on an axis going up, and for negative sine, you have to be on the axis going down, and then you just get over to that point. So aside from the sign of your a value in the front, the only thing that's going to be different is your phase shift. Okay, that's a good place to stop for today. We will finish the notes tomorrow, and then on Friday you'll have that in-class quiz. Okay. What's that? No, the homework will probably make due on Monday. All right, any questions today? How much time do we have left? 3 minutes. Okay, that was good timing.